I guess we can get started. Welcome back, everyone. For the announcements today, nothing too major except that our fourth quiz is due today. The fifth quiz is posted, but we expect this stuff on Thursday anyways. Also, we're working our way through the material pretty well. We're just about done with section 3.5, dealing with the chain rule. We'll probably spend most of the day, rather, we're not almost done. We'll spend most of the days in that section. And in case we run out of time, the application section 3.6 is just posted a little bit earlier. This one is kind of a nice application section in the sense that a lot of people are pretty familiar with exponential growth, exponential decay. And we're just really going to take a look at the concept for a second time that you've seen in college algebra content and to see how it really relates with calculus, since usually when you see this the first time, the calculus aspect of it is just totally missing. But now we can look at it from the entire point of view of what's the underlying differential equation and what's the solution to that differential equation, to ask and answer even deeper questions than we could when this first came up. But that's pretty much what we're going for. And for the upcoming quiz 5, it's kind of a review of these two topics right here. There's a product rule, there's a quotient rule, and there's a chain rule problem. Nothing too major, but similar kinds of topics we've been working on this week. I think that's all my announcements. Any questions at all, folks, before we get started? Okay, let's give this a try then. Back to the section on chain rule, let's spend some time here just as a kind of a refresher on what's going on whenever we do the chain rule. So I have the formula right here, but I should copy in. That's a nice formula, but it's not totally complete unless you specify the function. F of x, the original function, was f composed of g at x. Then once we had that function defined in this way, that's essentially where the chain rule comes up. It's a function composition we're dealing with. The g of x in part A was the cubic polynomial right here. And the f of x in part A was the power 103 function. But that could be anything. It could be a square root function. It could be an exponential function, a logarithmic function, and so on. But the process was identify what is what in this composition. First thing we would have said is g of x is a derivative that we do, oh, hang on, let me fix that. F of x is the derivative we do first. G of x is the derivative we do second, since it's the inner function. And f of x is the outer function. So viewing this formula right here, the process was first differentiate the outer function, and that's what we did when we took 102 for the power, 103 came down below as a coefficient. You insert the inner function back inside the derivative unchanged. So we just literally took all of that, dropped it back in. And then the next thing is, oh, I should be pointing here when I say you insert this and drop it in. I should be looking right there at the red dot. Then you multiply by the derivative, g prime at x, and that's what we did right here. That's the derivative being multiplied, and that's the derivative being computed on the next line. So chain rule is one of those processes where it's hardest to really see what the formula is saying, but once you get the pattern of attack and you maintain that same style of computing the chain rule every single time, it becomes a second nature kind of thing. We just need practice working with it. Well, any questions at all, folks, on looking at this a second time? Okay, let's get into a fresh problem then next. For part B, another weird looking function, we have 9 divided by the fifth root of a polynomial, 2x squared minus x. This is different than the part A because our function is not in a format where we would differentiate it. Even if it wasn't a chain rule problem, we would fix this before we got started. So first thing we'll do is write out that f of x. Fifth root here means we're really dealing with 9 divided by something to the power of 1/5, which is 2x squared minus x. And if we leave f of x in this format, then it's 2 rules. It's going to be the quotient rule first, and that's going to be annoying, a lot of work, and the chain rule all at once. But make one small correction here by manipulating the exponent. or set negative, you have 9 times 2x squared minus x, power negative 1/5. Over here, there is no quotient rule. We're trading out a quotient rule on the left for the constant multiple rule. Far easier to navigate. We can't leave the fact that this is a chain rule problem, but at least this is a nicer derivative to handle. Now that we're at this stage, we have to do the analysis of what is what. Usually it's not too bad, like we mentioned, to find the inner function. It's the function on the inside with the function composition. So this 2x squared minus x is a derivative we handle second for the inner function. And this part, power negative 1/2, that's derivative 1 for the outer function. And we're not too worried about the 9 because, again, there is another differentiation rule there, but it's just a constant multiple rule. When we go to differentiate this, we'll just copy in the 9 and then begin the chain rule process over here. And just to keep the color coding the same throughout these whole notes, I'll often color code inner function green, outer function blue. At this stage, we're ready to crank out the derivative. Go f prime x equals, right over here, because 9 is multiplying, we just copy it in. There we go, that part's done. Next, the 1 and the 2 here is just trying to indicate what order do you differentiate. We have to differentiate this power function first, which means negative 1/5 drops down in this way. The new power on the group is going to be 1 less than negative 1/5. So subtract 5 over 5 for negative 6/5. Then after that, we have to multiply by a new derivative. So that multiplication here is the chain rule aspect. Then finally, take your inner function, drop it into these open positions that we left, 2x squared minus x, in both spots. And that's step 1. Step 2 is just to handle that last derivative right here. Does that make sense to folks on putting all these down? Okay, I think the hardest thing to visualize sometimes about the chain rule is what happened with that, where it became negative 6/5, negative 1/5. But if you could train your eyes to see it essentially this way, the outer function was really y equals x power negative 1/5. And then when you differentiate that, you have y prime equals negative 1/5 x, negative 6/5. The only difference between this derivative and this one over here is that the input to the function was the whole quadratic polynomial, 2x squared minus x. So we just substitute it into that location. So we're really just extending all of our old differentiation formulas, like we see here, in this weird way. Well, we don't want to celebrate too soon. Don't forget, we always have to do that last derivative here. So our end answer is going to be just copying left to right here, negative 9/5. 2x squared minus x. I'll make the stylistic choice of just leaving that whole group in the numerator, so negative exponent. When we differentiate this, an easy mistake to make here is you do have to have parentheses. WebAssign is going to complain and say your answer's totally correct without the addition of those parentheses. So this would become 4x minus 1 when we differentiate that polynomial. Then here, this is a good stopping point. If you try directly type that into WebAssign, that would be a fine answer as well. And I think this is a pretty confusing problem because we had to work with exponent laws, get it in the right format. And then after that, the chain rule should look pretty similar to what we did on this one here. It was just a weird exponent, right? Negative 1/5 versus power 103. But the patterns, if you look in the color coding, was exactly the same on both problems. Any questions whatsoever, folks, finalizing this one? Okay, well, today all we really have is loads more of these. So let's try out the next derivative. Chain rule is one of those things where you really just have to practice it a lot to get the feel for how they all go. And this is one where it starts to get a little dicey. Notice what's going on here. If it looked just like this, That's a chain rule problem in that format because there's an outer function power 4, an inner function 2b squared minus 7. But throw that in, and it's, well, if there was a missing first factor here, that's a chain rule for the same reason. Put them both back in, and now it's product rule leading into chain rule. So we have to navigate both at once. So let's take our time with this one, break it down with our analysis, but first say, because of the multiplication here, that implies directly and immediately use product rule first. Does that make sense to folks on the product rule sneaking into this problem? Okay, let's write out our structure for a product rule. I'm going to drop the color coding on the product rule because the new thing here is really the chain rule. So I'll pick it up once we get to that portion. But we've practiced the product rule. Essentially, it's just write down a set of parentheses that go like this. Derivative on 1, copy the next factor, add a new term connected with plus, copy, and then derivative. So we're just moving our prime symbol over to the next factor as we go to the next term. Then copy these things down in the same direct order in both of these positions. So 2b squared minus 7. And hang on, don't forget it has power 4 on that. 2b squared minus 7 to the 4th power, b cubed plus 5b minus 1. And we can put a power 8 just on this parenthesis. But that prime symbol there, we needed a new inner parenthesis on that first factor by a red dot. Over here, we can just throw a power 4, like we mentioned, go 2b squared minus 7 to power 4. On this one, I think I'm going to need more space. Let me extend that. This one has a power 8, so we need another set of parentheses. Go b cubed plus 5b minus 1 to the 8th power. So this is the result of the product rule. It started off not great, and now it feels twice as bad, but we could get through it. It's just a lot of additional algebra we have to maneuver through. After writing out all of this, chain rule happens actually twice in this problem. It'll happen right here, and it'll happen out right here. Both derivatives are still chain rules. Analyzing this one, inner function is 2b squared minus 7. Outer function is the power 4 function. And then over here, there's a new inner function. And the outer function this time, highly similar. It's just the degree 8 power function. And on this line, just to be specific, we're using the chain rule twice. So let's give this a try on the next line. I'm just going to copy down a long chain of equalities so we don't have to write G prime multiple times, unless you would like to. It's more of a stylistic choice. Now, starting on this group, let's work out the chain rule here. 4 comes down when we differentiate the outer function. New power on that group is 1 less, so power 3. We multiply by the derivative of something else. Now at this stage, grab the inner function, put it in those last 2 positions. Feels pretty methodical, but that's the way it should be. Learning something like the chain rule, you want to try to think about it and do it exactly the same way each and every time until you get just really fluent with it. Then you can start doing all the little shortcuts and just tricks and those kinds of things. By the way, one shortcut would be is when I put 2b squared minus 7 here, I often just compute the derivative and throw it into that location, 4b, and call it good. So if you take that shortcut, I'd say that just indicates you've used chain rule a lot and you're getting pretty fluent at seeing how it goes. But when you're learning it, this is a really good and powerful extra step just to break it down into stages. It's complicated enough. So I'll avoid any of those shortcuts, really just mentioning it to say you're welcome to use those if they seem preferable. Over here, we're copying, so b cubed plus 5b minus 1 to the 8th power, copying all the way to this stage, plus 2b squared minus 7 to the 4th power. And now another chain rule over here. Same exact analysis, take 8, drop it down. New power in that group is 1 less for a power 7. And because it's a chain rule, multiply by the derivative of something. That something in the both positions is inner function, b cubed plus 5b minus 1, copied, and then over here, it's copied in, but then we also differentiate. So it's a humongous mess now. It got worse in the product rule and even worse in the chain rule, but it does actually clean up. It's kind of surprising in a way. Let's now finalize our final derivatives here and see what we get. So let's see. Looks like we can drop this outer parenthesis and go 4, 2b squared minus 7 cubed. Derivative of this is just times 4b. The negative 7 will go to a 0. And then back to copying all the way to that point. b cubed plus 5b minus 1 to the 8th power. 2b squared minus 7 to the 4th power. And then copying all the way to this point now. And hang on, let me back up one step. We can also drop those outer parentheses as well if we would like to. Oh, that was supposed to be an eraser. Let me try again. So drop that parenthesis, copy from this point on until the derivative. So now it's times 8. b cubed plus 5b minus 1 to 7th power. And finally, all the way over here is our last derivative to compute. This time we need parentheses on this one because it's going to be 2 terms altogether. So we'll go 3b squared plus 5. And then assuming everything was copied down directly and accurately, this should be our next line. How's it look to folks so far? This is one of those things where if you do a problem like this in WebAssign, definitely go slow, stare at it, because you'd be surprised how easy it is just to forget to say, copy power 8 down to power 8, power 4 down to power 4, all those little details, and there's quite a lot of them. If we drop one, our answer's way off according to WebAssign. If you dropped one little thing on an exam, we grade on partial credit. I'm mostly looking at how well you know the concept. And by the way, this one simplifies. It simplifies a tremendous amount. But I believe WebAssign would have taken this as an answer. So I'll leave it up to the class. Should we simplify this one just for the extra practice with algebra? All right, everyone in the classroom saying yay. I didn't hear any objections over Zoom, so let's give this simplification. It's an acceptable answer at this stage, but simplifying this, well, it depends on what you mean exactly. For me, if I have a polynomial like this, simplifying is not expanding it out. That would take all day. Simplifying here usually means factor it as much as possible. And that's just the right thing you would want to do in chapter 4 anyways. If this was an applied problem, we're looking for local minimums and maximums, this has to be factored as much as possible. So now, if we're factoring it, we are looking for a greatest common factor on this thing. Let's do this analysis in the middle to explain the factoring step. So there's just 2 terms, and across this term, we're looking for something that divides both. We have 16 here and 8 here. So from those, we have a greatest common factor of 8 can factor out for the constant term. Now go to the next level of terms. There's a group 2b squared minus 7 cubed here. 2b squared minus 7 to power 4 here. And an interesting question with greatest common factor is, do we take the lowest power or the highest power? What would you all say for that question? Lowest, good call, absolutely. Notice how it had to kind of hurt your brain a little bit. Greatest common factor means you factor out the smallest thing. And when we do that, let's take that out. 2v squared minus 7 cubed. What it means is when you actually factor this out, you're dividing it in this term, so it's a clean cancellation. You're dividing it in this term, leaving 1 power. But if we went to power 4, it would not have divided evenly into this one. And so that's the weird thing about greatest common factors. You look at the common factor, take the lowest power. Then on to the next level of terms. There's a 4v here, but there is no group that contains just a multiple of v. So we have to skip that one. Move over to this, v cubed plus 5v minus 1. It occurs here as well. We take the lowest power, power 7. V cubed plus 5v minus 7, or excuse me, minus 1 to the power 7. And it looks like beyond that, because we considered all the factors in the very first term, that's it for the greatest common factor. Now the next step, we'll actually factor it out. Here's what it'll look like. Take all of this, and this connects here just for clarity. 8, 2v squared minus 7 cubed, v cubed plus 5v minus 1 to power 7. Open another bracket, and we are literally just dividing. There's 4 and 4 here for a 16, so when we factor out 8, it leaves behind 2. Then 2v squared minus 7 cubed is a clean cancellation with that factor. But this one's to power 7, so it leaves one factor of that group. We have 2 times v cubed plus 5v minus 1. So now go over here to the second term and just redo that entire process. The constant 8 cleanly cancels with this 8 here, so it's gone. And I probably should start by writing down plus to plus in that way, getting the middle term. 2v squared minus 7 cubed cancels here, leaving one factor, 2v squared minus 7. And this one, v cubed plus 5v minus 1 to the 7th power, obliterates this, so it's gone. That's kind of nice. But that one's a survivor, 3v squared plus 5. So that's simplifying a little bit. All we did was factor it, but it does clean it up a lot, getting to that point. The downside of this is once you start simplifying a little bit, you'll notice this can go on for some time, right? Because all of that simplifies next. Let's work on the final simplification of this. I'm copying all the way to the bracket right here. 8, 2v squared minus 7 cubed, v cubed plus 5v minus 1 to the 7th power. Now over here, 2 distributes in, so 2v cubed plus 10v minus 2. Over here, we can FOIL this out. So here to here is going to be plus 6v power 4. Here to here is plus 10v squared. Then new set of arrows. That's negative 21v squared. And that would be negative 35. Almost there, folks. Again, just for emphasis, if this was a real, say, quiz problem, web assignment problem, exam problem, I just want to emphasize as we see the algebra kind of explode on this, this is a full credit step right here. And we're simplifying it down mainly because this will be a helpful technique once we get into chapter 4. Mainly a review of algebra problem that we're working on. So last thing to do is combine all of those like terms. So copying up to the bracket, 8 2v squared minus 7 cubed, v cubed plus 5v minus 1, 7th power. And I'll organize this by combining like terms descending on the degree of v. Only one term with v power 4, so copy that one in. Now eyeball the v cubes, there's only one. Now for v squared, 2 of those, so these combine to negative 11v squared. We're at v power 1. There's one term here, and there's a lot of stuff. It's kind of hard on my eyes, but I think it's just one term, plus 10v. Now for constants. Negative 2 minus 35 will give us negative 37 altogether. And that's a pretty big polynomial over there. But at least this answer, if you're in chapter 4, trying to look for the local minimums, local maximums of that function, that's the more useful answer, far simplified. And this would be the hard answer to work with over here. Well, we did it, folks. This is a tough problem because not only did we do chain rule twice, we had to combine it with the product rule as well. Next problem is going to, we'll do the same kind of thing. We're going to do chain rule with quotient rule next. Any questions at all, folks, with the full write-up of this one? Okay, let's try out the next one then. Next one is, well, lots going on. Recall in the last one, we said we had to use the product rule first. That's not the case this time on this one. This one requires chain rule as the very first step because the function on the inside is a quotient. When we go to differentiate that, that's the part that's going to be the quotient rule. But this is an inner function, which means we do that derivative second. And that's the use of writing down the 1 and the 2. It's just a way to kind of give our eye a little bit of a guide on how the next steps go in chain rule. So that's function 2, the inner. Power 6 function is function 1, derivative 1 that we'll do. That's the outer function. And this configuration, we use chain rule first. When we go to differentiate the inner function, we'll absolutely have to use quotient rule on that one. That implies use quotient rule second. So that's going to be the order of the differentiation property operations on this one. And honestly, if we try to contortionistically use quotient rule first, no idea how that would even go down. So sometimes once you get really fluent with this, it becomes pretty natural in the order that you do have to do these things. We just need to practice. So here's our answer we're going to come up with, h prime at t. We begin with the chain rule analysis where it says differentiate the power 6 function. 6 comes down. New power is going to be to the 5th power. Then we multiply by the derivative of something. Inner function goes in both of those parentheses. So t squared minus 3, t squared plus 3, and again in the second placeholder. Okay, we're ready to go. And when it said use the quotient rule second, here's where it occurs, in this location right here. We have a big thing right here, right in front of the quotient rule. So one strategy that you could use is break up the problem. Let's just rewrite this as y equals t squared minus 3, t squared plus 3. We don't have to break up the problem. And the very last problem, we didn't at all. We just did it all in line, step by step by step. But if you feel like it's good to separate things out and just plug in answers back, this is a great stylistic way to just format this derivative. So here, we're going to do that derivative and write out y prime. This is a good view of the quotient rule. You set up parentheses as if you're doing a product rule. But one change is you put negative in the middle, and you divide by something squared in the denominator. Organization here says take t cubed minus 3. It only goes into 2 spots. In this factor, and in this one. Or first positions is usually what we say, first position across each term. Then the denominator, t squared plus 3, goes everywhere else. Now all we have to do is work out this derivative here. So where the red dot is, derivative of t squared minus 3 will give us a 2t. Minus 3 goes to 0, being a constant. So that derivative is totally done. Multiplies against t squared plus 3, so let's copy that in. Subtract t squared minus 3. Derivative of this one, another 2t, so times 2t here. And t squared plus 3 squared down below. We're almost there. We need to plug all of this back inside there. So let's simplify it a bit just to make the substitution look a little less overwhelming altogether. Distributing 2t into the group by the red dot gives us 2t cubed plus 6t. And on this one, we're doing a distribution on the left with the negative sign, distribution on the right from 2t. This will give us a negative 2t cubed altogether. Then just adjust those arrows slightly. Negative 1's multiplying here for a positive 3. Multiplies by 2t, so a positive 6t. Does that look right to folks on this distribution here? Awesome. It always, to me, looks weird when you're distributing simultaneously from the left and the right, so that always is a good one to go careful on. Denominator is still t cubed plus 3 squared. Excuse me, t squared plus 3 squared. And it's essentially there. We have a big cancellation in the numerator. And we have like terms at the same time in the numerator. The result is now 12t division by t squared plus 3 squared. So this whole thing plugs into that entire thing right there. So in a certain sense, if you like the 2-column system, this is a pretty nice way to compute because it took kind of the tedium of this entire derivative, shoved it to the right, and then we fixed it. And then we're just going to take the output, drop it back in on the left where that's our clean answer. So h prime at t is 6. Let's do something a little extra on this one as well. That power 5 can raise the numerator to the 5th power and the denominator. So let's do just that. T squared minus 3 to 5th power. T squared plus 3 to 5th power multiplies that whole thing, 12t, divide by t squared plus 3 squared. Let me just slap it with the highlighter to say that's the substitution connecting through with the yellow. And final step on this one, h prime at t is first going to be 6 times the 12 here for a 72 times t squared minus 3 to the 5th power. And then the whole reason we took this power 5 and raised the numerator denominator to the 5th power is because t squared plus 3 to 5th power is the same base as this one, t squared plus 3 to the 2nd power. So those also combine and give us the answer as simple as possible, t squared plus 3 to the 7th power. And that's our total derivative on this one. In my opinion, part D looks like it's the harder question, but the one we did just prior with a product rule into a quotient rule, that one was way harder just because there's so much stuff you have to consider all at once. But we did it, folks. This is the product rule and the chain rule, excuse me, the chain rule and the quotient rule, rather, being used simultaneously. And if we really wanted to, if we wanted to be super creative, we could come up with a problem that uses every single differentiation formula that we've seen so far. Product rule, quotient rule, chain rule, constant multiple rule, derivative of constant is 0 rule. We could just combine every single thing, but we'd have to have a reason to do that. There are a lot of functions that we see in practice look like this, for example. If it's going to get super, super complicated, well, we would have to be fluent with calculus already dealing with those. So this is a pretty routine kind of problem for this class as far as it goes for being a tricky one. It wouldn't get too farther out of the line than this one. If you're doing problems in an exam, they look a lot more like, say, this one or this one up here, more routine exam problems for chain rule. But sometimes things get messy, so we're looking into those problems as well for extra practice. Well, let's try out the next problem then. Unless any questions or comments so far. Okay, so next one to try is example 3, Example 3 is actually a pretty big problem. In example 3, we come up with a really powerful differentiation formula. And this one was being asked about in the prior sections. In the prior sections, we had a derivative that goes like this. Derivative with respect to x of the base e exponential function is fantastic. You get e to the x. But this new theorem, the reason it shows up in section 3.5 is you need the chain rule to prove that this derivative is true. So the author put it off till now. If you take the derivative of base b to the power of x, you get base b to the power of x, much like we got e to the x, times natural log b. So this is the full and general formula. This formula works for any base whatsoever. And if it happens to be base e, natural logarithm e is 1. So this is the only time that actually simplifies as a formula. So the formula on the left is just a bigger formula than the one we see on the right. This is like one base. This is all of the bases, essentially. Considering, of course, your bases have to be positive and they can't be 1. So we're going to practice with that formula there. And what makes this formula really complicated in a certain sense is when you look at all this stuff, it's hard to tell exactly what's going on with some of these. The first two problems almost look identical, but it's up to us to tell the difference and apply the right differentiation formula. So let's break this down into a 3-column system this time. We're going to consider the 3 functions simultaneously. Y equals x cubed, y equals 3 power of x, and y equals 9 to the power 3 minus 5x squared. Okay, on the left, this one is not too bad. This is just the power rule. And what happens with the power rule is we go y prime equals the power, that's why it's called the power rule, we operate on the power, comes down as a coefficient. The new power in this derivative is 1 less, so it drops down to power 2. And then we're done, we are on our way. But notice the danger here. If we move on to the next function and try and maintain the same pattern, we have a big problem. X does not come down. The new power is not x minus 1 any longer. And that's because this one is just a totally different function. This is, because of that part right there, an exponential function. And because it's an exponential function, we have to use this property over here. Let's just box that out to convey that x is what forces it as exponential, forces us to use this formula. And so we'll write out, let me fix this part. The base is b, it occurs here and here. Our base is 3, so our derivative goes y prime equals 3 to power x multiplied by the natural log of 3. So that's our new derivative, the general derivative of an exponential formula in action on this problem here. Again, the purpose of this problem is to tell the difference between this line and this line. This is a good one to come back to, stare at a little bit when you're doing problems in the homework. If you're having any issues with these exponential functions, it could be just this small change. X cubed, 3 power of x. Honestly, to my eyes, they look almost exactly the same. But once we train our eyes to spot the difference, we get away from that trick there, and it's not too bad of a derivative. This one is the tricky one for sure, because not only is it using this rule up here, the base is 9, it is an exponential function, but it's also a chain rule problem. We have an input that's not just x. Anything in addition to x gives us a chain rule. One thing you can do to this problem is reformat it. Y equals base 9. If you want to think of the ordinary power patterns of how the chain rule goes, you can think of this as function notation. The base 9 exponential function takes an input x. That input x is 3 minus 5x squared. And that's the inner function right here. So again, this is really tricky in a certain sense. Before we finish this one off, let's go back to a nicer one. Because with a new derivative like that, you want to compare against what we just did with what we're about to do, so we can really spot the difference. Okay, so here's our little guide over here. It's bigger than I thought. Over here, this is the problem that we're about to differentiate. And the analysis on this one will not call the power the outer function any longer. That's the inner function that goes inside the 9 power x exponential function. So patterns are great, but this is a case where the pattern breaks down. A power is not always the outer function any longer. This time, excuse me, I said that backwards. The power 103 is not always the outer function. In this configuration, that power is the inner one. Does that make sense so far?
Is it fair to say that if there's a plus and negative or negative in one of the in part of it, and that's the inner? Or if it's just bigger, then it's the inner.
Pretty much, yeah. If it's just bigger. For example, if it goes 9 power of x, no chain rule on this one. But if it goes, well, to save that thought, if it's 9 power of x, it's pretty much just this problem, right? And if it is y equals 9 to the power of 2x, that alone forces in, it's a chain rule problem out of nowhere. Anything that's in addition to x gives us that chain rule. Does that make sense with that question there? Awesome. Other questions so far?
9x to the power of 2x.
That absolutely is a thing.
Yeah, that would be product.
It would actually be a wild one. That's a good derivative. So the derivative you mentioned, let's take a look at that one separately. Y equals 9 to the power of x to the power of 2x. This one requires what our author would probably call a little bit of ingenuity to get through this one, but it's one that we can try out. It will require a technique of logarithmic differentiation. So there's little extra stuff going on that one. But other questions so far with looking at that as an inner function? Okay, again, this is a good one to really spend some time on, really train your eyes on this, because these problems here were so common at the start of the notes, but if you change the function, the pattern looks totally different, even though it really is the same pattern. It's just a different kind of function this time. So that's the inner function. The base is the outer function. Well, what is that function specifically? The outer function is really y equals 9 to the power of x. And we just happen to put in something way more built up than x itself. That's why it's a chain rule problem out of nowhere. Well, if we go to differentiate it, let me scroll back up to the top so we can consider that formula. It really is the same exact pattern that we would do with ordinary chain rule. Follow this new guidance that is only relative to exponential functions. It says differentiate this first, which means we're using this structure. The derivative of 9 power of x, much like 3 power of x, goes 9 to a power times natural logarithm of the base, which is 9 this time. But then it is a chain rule problem, so we go times the derivative of something. So that's the setup so far. We come back over here, drop the inner function in 2 spots. 3 minus 5x squared here, 3 minus 5x squared here. And now the problem is almost done at this stage. We can rewrite our total answer by saying y prime equals 9 to the power of, you can leave those parentheses there if you like, but ordinarily people would drop them at this stage, 3 minus 5x squared. Then we have natural log 9. Then we take the derivative of 3 minus 5x squared. That one's not so bad. The 3 here vanishes, being a constant. And this portion will just become a negative 10x. So those are the three different functions to consider and be very, very careful with. On the left, this was really what we did in section 3.3, the good old power rule. In the middle, we're using the theorem right above that informs us how to differentiate any exponential function whatsoever. And then on the right, we're combining our new formula, that one, with the chain rule all at the same time. Any questions or comments whatsoever, folks, seeing either one of those? Okay, and now for the other question, what about this thing? This one is a little bit of a pattern breaker. On all the problems we've seen, we don't necessarily have something that's going to help us whatsoever with this one. Because look at this theorem one more time. It says if B is a constant, then that's how the derivative works. But what's playing the role of B on this one? It's that, and it's not constant, that varies. So this theorem is actually irrelevant to this entire function as it stands. There's a way to get out of this, and this is a preview of section 3.7. To differentiate a function like this one, this is a horrendous format. What we would actually do is take the natural log of both sides of this. We would go natural log y equals the natural log of that entire thing on the right, 9 power x, to the power 2x. And then the immediate questions we would have here is, how in the world does the natural log even help us? Really, this is a pretty strong preview of just logarithmic properties. Yeah, go ahead. It doesn't quite cancel it. Yeah, exactly. It becomes a coefficient. So the whole struggle with this was 2x being a power. But like you said, the natural logarithm will correct that just immediately. Let's write down the formula. Natural log of a for anything to power p is the power p times the natural log of a. So that's the logarithmic power property, rather, that's relevant here. If we apply it here, we go natural log y equals, this 2 power of x comes down. We have now natural log of 9 to the power of x. But notice if that happens, x comes down as well. We'll just use it twice. It applied here, and it's going to apply here all at the same time. So next line, natural log y is x is coming down, combined with the 2x here. So now 2x squared. Natural log 9. Way different function now, right? The only trouble is if we took the logarithm of both sides, we have to undo the fact we took the logarithm of both sides. But now this line can be differentiated. It requires other new techniques, however. We differentiate the left-hand side, we need to use the property that the derivative with respect to x of the natural log x, this is what makes it a real bona fide preview of 3.7. We've never actually said that derivative. But you know what? It's great. That's it. The natural logarithm of x just turns into literally flip x to the denominator and you're done. But that's only for this logarithm. Just like up here, there's the nice derivative for the exponential, and then the not so nice derivative for any exponential. There's the nice derivative for the natural logarithm, and then the not so nice derivative for every other logarithm. So that's something we'll take on as well in section 3.7. But now that we have that, I think we can get rid of that now. We can differentiate both sides simultaneously. I'll leave it up to the class, though, at this point. This was more of a discussion of why doesn't this function really fit into this problem? How would we continue to differentiate? It is a preview already to this stage, and if we keep on going, it is a larger preview. So I'll leave it up to everyone in the class. Should we keep on going to finish it off, or would we rather go to the next problem? Your choice today. Sounds good. It's weird to just leave something sitting on the table. So let's correct this, or let's finish it out. we need to take the derivative of the left-hand side. So I want to carefully write that in as bracket natural log y prime. We also have to differentiate the right-hand side as well. But notice natural log 9, that's a constant. This is not a bad derivative. Let's rearrange these constants as 2 times natural log 9 times x squared. So we're just taking the derivative of both sides simultaneously. The right-hand side is tricky because we have to recall this part is constant. The formula here doesn't apply to natural log 9 because of the lack of the variable x. So left-hand side is tricky though. This is a really, really strong look at the chain rule right here. So when you look at the derivative of this altogether, there are 2 functions now. The outer function, well, let's do the inner function first, is y. It's inside the natural logarithm. It is a function of x. That's what it is originally. That means this one is derivative 2, the inner function through the chain rule. The natural logarithm right here will be derivative 1. That one is, oh, hang on. Yes, the outer function I got mixed up out of nowhere. So y goes inside the natural log, make it an inner. Natural log is then the outer function. We're informed on how to differentiate that. And then how do you differentiate y? That's the original question, right? This looks almost circular, but I assure you it's not. So we have a chain rule analysis on the left. We have a constant multiple rule analysis on the right. We're ready to now hit this with our derivatives. Let's go carefully on the left-hand side. We first differentiate the natural logarithm. This is the structure for that. It takes whatever your input is, drops it to the denominator. So on this derivative, we go 1 over something. Then, because it's a chain rule, we multiply by the derivative of that something, whatever it was. The something is your inner function y. It'll go here, there it is, and it'll go there. And as it stands right here, it says y prime. That's our goal, to compute for y prime. We now have an equation for which, if we solve for y prime right here, we have found the derivative in this strange roundabout way. Logarithms are just weird, but that's the left-hand side. Any questions so far, folks? Analyzing it at the moment? Right-hand side, a lot better, right? The constant is the tricky thing about it. We'll go 2 natural log 9, unaffected by differentiation if you're multiplying as we are. Differentiate x squared, that's just a times 2x. So the right-hand side is all set. Left-hand side, kind of weird, but let's rewrite this. I'll leave y prime on the left here. All I've done is drop parentheses. A parenthesis with a prime just says differentiate the function on the inside. There it is. At the same time, I'm going to multiply both sides by y, clearing the denominator. There it is. Multiplies all of this stuff, which is now 4, natural log 9 times x. And the moment we take this, that was the original question, but it's also the inner function. We can expand it over here to say once and for all, the derivative y prime is the entire function y, which was 9 power of x to the power of 2x. So there's that function. Multiply by this, which is 4 natural log 9 x. So that's the derivative of this one. Pretty bizarre in a certain sense. But any questions at all, folks, finalizing this problem? Okay, so that's dealing with derivatives with logarithms. Again, making this one a pretty big preview section. But it's appropriate because if we're differentiating exponential functions in this purple box, Well, logarithms are just the inverse to those. So we need to know this derivative if we're discussing that derivative as well. But let's see what else, other new adventure we're getting into. Unless there's any questions at all, folks, on this one. Okay, so for our next one to look into, this one's kind of a throwback from a while ago. We have a function y equals square root 9x minus 8. And all we want to do on this function is find the equation of the tangent line at the point 1, 1. Now, we've said this before, but I want to just re-emphasize. If you're thinking, well, it's a tangent line problem, so I want to go back to section 3.1 and do it this way, really hard on this problem because there is so much going on the moment it's a chain rule problem. This is a tough derivative to do from very first principles. So I would encourage you, treat yourself to some differentiation formulas. You don't have to work the hardest way possible each and every time just because it was a tangent line problem. But I get the thought, if we did a tangent line this way the first time we did it, it kind of sticks in your head, right? It's almost tempting to break out the limit definition. But that's working in a very, very painful way. Here's a different approach. Let's take this, analyze it from the point of view of, well, let me say again, let's just correct the notation on this. Let's rewrite it as y equals 9x minus 8 power 1/2. And it's kind of an ordinary function now. Because x is on the inside here, it tells us that this 9x minus 8 is our inner function, so derivative 2. The power 1/2 on this one, that's our outer function, so derivative 1. So going to calculate the derivative on this, let's go in Leibniz, dy dx would be first standard chain rule this time, kind of refreshing after the last hard derivatives we did. 1/2 drops down. New power is 1 less, so negative 1/2. We open another placeholder to accommodate what's going here through the chain rule and drop in inner function. 9x minus 8 here and here. At this stage, our derivative is practically done. Copying up to here, we have 1/2. 9x minus 8 power negative 1/2. This derivative is 9. So times 9, which means the whole thing could be rewritten with the 9 in the numerator, 2 in the denominator. If you wanted, you can also move that to the denominator. We would have power 1/2 here, which means it's just a square root. But if you left your answer in this format, that's okay as well. This is just a little bit easier to compute with the next step. In the next step, to get the tangent line equation, you have to use that first coordinate to find the slope. But that's really most of the work right here, getting the derivative out. Does it look okay to folks on that stage? Okay, so for any tangent line equation process, this is basically step 1. Obtain the derivative. This is now the slope of the tangent line at any x value that's in domain, plenty of them are not. Step 2 is produce the slope. The slope you can continue to call m. It's dy dx. But that's the slope. Dy dx is the slope at any point x. We evaluate it when x equals 1. X equals 1 is from the first coordinate right up here. And that means on our next step, we have 9 over 2 times the square root of 1 goes in there, so 9 by 1 minus 8. So this is just the root of 9 minus 8, which is the square root of 1, which is 1. And that tells us the whole slope is just 9/2 altogether after simplifying. So now we have a slope, we have a point, and if you'd like, you could call this x1, y1. And that takes us to step 3, just build out the equation. So standard way is y minus y1 is slope m times x minus x1. It's not the only way, so if you've learned this in a different way, using maybe the slope-intercept form of the line, that would work out totally fine as well. We take our 9/2, drop it inside there, and let me see if I can zoom out just a touch. Grab those coordinates for x1, y1. So we have y minus 1 equals slope m, 9/2 times x minus 1. And if we go to the right here, this is, well, we're going to get a negative 9/2. So let's call this 2/2 equals 9/2 x minus 9/2. And finally, here's our ultimate expression we were going for. The tangent line equation should be 9/2 x and then minus 7/2 after adding the negative 2/2. Let me box this one out just to convey that's what we were going for. And we did it, folks. This is coming up with a tangent line equation in the context of we had to use the chain rule to get started. Next thing we should do, imagine maybe it's a quiz problem. Just plot this and see if it's accurate. Y is 9x minus 8, power 1/2. Definitely has a domain issue, right? So it starts right here at roughly 0.888. Next thing we throw in is y equals 9/2, x minus 7/2. And the coordinate we're checking for tangency is at 1, 1. At 1, 1, let's get a really good look at this. That really does look tangent. But these curves are deceptive. What you really want to do is go to 1, 1, zoom in on this thing, and the pattern you should see is the lines get closer and closer the more we zoom in. The reason for that is this is a complicated function, but the tangent line equation is the best local linear approximation of the more complicated function. And it really looks like that. The more we zoom in, the more we just see blue, the tangent line equation itself. So we did it, folks. That's the full process on this one. Next problem we're going to take a look into is going to be the application at the bottom of these notes. But any last questions or comments at the moment?
On the test, will we always be able to use a derivative instead of doing that whole long thing we did at the beginning?
Yes, absolutely. So even on exam 2, even though this is on exam 2, if this problem showed up, just use this process and you'll get absolutely full credit. Other questions so far? Okay, well, we've done loads of derivatives. The hard thing about derivatives is to say exactly what are their uses in the physical, biological sciences. And this is one problem that gets us close to thinking along those lines. So let's take a look at this. This is some kind of capillary, or it says it's the artery, a little bit more important here. It tells us next, the speed S. So we have a function telling us the speed of blood. The speed S of blood, that is r centimeters from the center of an artery, is given by this formula. So we're really just tracking one platelet of blood, essentially. If it's this distance away from the center of the artery, it gives us a certain speed, visualized by that arrow right there. The closer it is to the center of the artery, the faster the speed of that one platelet of blood. So that's what's being conveyed by this first sentence right here in the image. So that lowercase r you see right here, that's just how far away the blood is from the center of the artery. Uppercase R is the total radius of the artery. Okay, so we've got a mysterious constant that makes this model accurate. We have R, the radius of the artery. S is measured in centimeters per second, so interesting unit. But now there's more drama in this problem. The radius of the artery just depends on what's going on with your metabolism. And it says here, suppose a drug is administered and the artery begins to dilate. So someone took some crazy drug, maybe metformin or something, and it's affecting your metabolism, your biology, and this R is shrinking now. Well, I believe dilate is shrinking. Let me know if I got that backwards. Hang on, no, dilate means expand, doesn't it? So someone was administered a drug and this artery is expanding. R is getting bigger is the better way to say it. It begins to dilate at a rate dr dt, the rate of change of the radius of the artery with respect to time. And that right there tells us immediately R is a function of t, time. So when we looked at this problem, it's a lot more going on than we really realized until we saw that information. This is a chain rule problem right here because there's a power 2 function and inside is another function that changes with time. Next, it tells us at a constant distance r, that's kind of nice. And let's also record this one with the highlighter. They're telling us what the constants are in the problem, which will inform us how to differentiate. So we're imagining the blood isn't just not going to change where it is with respect to the center. Find the rate at which S changes with respect to t. What they're asking us to do from this statement right here is compute dr dt. For all of that information right there, we want to know what is the rate of change for the way that actual artery is being dilated. Or hang on, let me try again. Find the rate at which S changes. That was a mistake here. If it says S, we want ds dt. That's worthy of copying down, just as a quick fix there. Find the rate at which the speed of the blood changes with respect to time, so ds dt, for all these values right here. And we were being told the artery is dilating at a rate dr dt, and dr dt is positive. That alone tells us dilating means expanding, growing, only because that was positive. So let's give this a try. First thing we'll do is grab the model up here and write S equals, let's expand this out. Take C and multiply CR squared minus C lowercase r squared. After that, we're going to compute ds dt. But with all the information that we've been specified from here and from here, tells us that this whole thing is a constant. So that's really informative for us. It's going to tell us how to differentiate. In front, C is also constant, so a constant multiple rule is coming up as well. And now next thing, R is a function of t. So when we're over here, this R, that's an inner function out of nowhere. So let me change that color. We'll say that this is derivative 2 we take, the inner function. Power 2 function over here, that's derivative 1 we take, the inner function. And now we're ready to compute. It's a pretty messy problem, but anything that is a good application is usually pretty messy. Real life is just messy, essentially, I suppose. Our derivative is ds dt. So let's go left to right and crank it out. C is a constant multiplying, so it's unaffected by the constant multiple rule. Here, we take the derivative of the inner function, which means 2 comes down as a coefficient. New power on that whole entire group is power 1. And as per the chain rule, we multiply by the derivative. In Leibniz notation, I'll indicate it this way. Instead of a prime, I'm going to go d dt to be specific on what the derivative is in that way. So at the moment, this is how we did every single chain rule. I've just exchanged Leibniz notation for what was a prime over here. Grab your inner function, dump it into those placeholders, just like before. Then our derivative now takes on the form 2c times r. Over here, this is d dt of r, but that's just a derivative in Leibniz notation, which could be rewritten as dr dt. At this point, it's all about plugging in all of that information here. I'm not sure what a good color coding is. Let's go with gray. So if we can plug that information in, we'll be all set. So next line, we have 2 times this coefficient C, 1.76 times 10 to the power 5. I'll write my exponential notation in this kind of way. Excuse me, my scientific notation that kind of way. We're evaluating the derivative where the radius of the artery is 1.2, 10 power negative 2. And at the time at which the rate of change for the artery expanding is this quantity, 10 to the power negative 5. So let's dump this into a calculator. Altogether, we have 2 by 1.76 by 10 power 5. Then let's see here. Let me double check I got that copied in. Okay, 1.2, 10 power negative 2. I could have saved some steps and said that's 10 power negative 7. But Desmos doesn't care, so let me just type it in verbatim. And we get this as a value, 0.04224. The original function S was measured in centimeters per second. So we would say that this is centimeters per second squared. So this is the velocity at which the radius is expanding if this was the speed, and all of that information right here would apply. Lots going on with that kind of problem, but I felt like we had to do at least one good application in this section, or else it's really hard to connect what the chain rule is trying to convey, unless we see it in a real applied problem like this one up here. So that's what's going on with blood, but for this specific information that was provided. Any questions at all, folks, finalizing the application? Okay, well, we did it, folks. The chain rule is the harder section, I would say. And for the purposes of getting prepared for exam 2, probably the problems you want to review the most would be in sections 3.3, 3.4, 3.5. That encompasses almost all of our differentiation formulas. If you get pretty fluent on how those go, you'll be doing great on this next upcoming exam. But this will be a good stopping point for us. We'll look into section 3.6 next time. Have a great weekend, folks. And if you have any questions, I'll be happy to help out. Take care. Any questions? Yeah.
Look at that, and tell me what I did. I'll figure it out.
Yeah, absolutely. So 2/7 came down. That looks good. New power is going to be subtract 7/7. So that looks good. You know, the negative shouldn't be the problem on that. And then inside x5 minus x cubed minus 1, then that would be 5x power 4. It should be, looks like it's that 3 right there. The 3 would come down, and then the power would be 2.
Oh, duh,
Yeah.
Just typed it wrong, okay.
Yeah, you've got the idea, though. That's the important thing.
Okay.
Yep, absolutely. Yeah, I hate that. And sometimes with web-assigned kind of systems, you get paranoid that the system is bugged or something small like that. Yeah. Have a good one.